I'm on location outside San Antonio, Texas, where a construction crew is getting started unloading equipment to begin work on a new sewage lift station. This area may look rural now, but it's one of the fastest developing parts of Texas. New homes and new businesses require new utilities, including sewers, to keep up with demand. And in this particular location, those new sewers need a new pumping station to get the wastewater where it needs to go. Most people probably couldn't guess the path their dishwater or flushes take once they're down the drain, but I've teamed up with the San Antonio River Authority to give you an up-close view of one of the most important steps in the process. Come nerd out about construction with me and follow along the project from the very first scoop of dirt to starting up the pumps for the first time.
I'm your host, Grady Hillhouse, and this is Practical Construction.
The excavator's already breaking ground for the construction of this new lift station. Sewers normally work by gravity. They rely on sloped, underground pipes to carry wastewater away from homes and businesses toward the plants that clean it up. But wastewater treatment plants are major capital projects, and we don't build them everywhere, so there's not always a treatment plant located downhill from populated areas. In some places, it's necessary to pump sewage up to a higher elevation. That's the dirty but critical job of a wastewater lift station. This particular project is an expansion of an existing facility. When it's done, the new lift station will operate together with its neighbor here, increasing the capacity of the sewage system as the surrounding area grows. It will also create some redundancy by allowing either station to be temporarily shut down for maintenance during periods of low flow. Because sewers work by gravity, they're always sloping downward, so the end of a sewer pipe is usually deep underground. And that means this lift station starts with a hole. A big hole. The bottom of this facility will sit about 30 feet or 9 meters below the ground, so this crew has a lot of work ahead of them. This soil is mostly clay, meaning it won't work well as backfill. Clay is difficult to compact. It shrinks and swells with changes in moisture content, and it tends to settle over time. So the engineers on this project specified a more suitable backfill material that will have to be brought in when the time comes. For now, the native soil from this excavation will have to be hauled away in trucks. These in-dump trailers can hold more than 20 tons of soil each, and it's going to take a lot of them to carry all this clay to dispose of off-site. One thing to notice about the hole, the sides aren't vertical. Safety regulations require that the sides of deep excavations be sloped to reduce the chance of a collapse while people are working inside. But that presents a problem, especially on a narrow construction site like this one. The deeper you dig, the less room you have to work at the bottom of the hole, since the slopes take up valuable space. On this site, there just wouldn't be enough area to get the vehicles and materials around the excavation if it were to go to full depth with sloped sides. So this hole has two parts. The first stage goes down 10 feet or 3 meters and uses sloped sides to avoid a collapse. The rest of the excavation will have to be supported using structural shoring. These blue parts being unloaded from trucks are part of a slide rail system that will hold the walls of the hole open as the crew continues excavating downward. The system includes steel plates called panels and vertical rails that make up the four corners of the box. The outer panels stay put, while the inner panels will eventually slide downward as the hole gets deeper and deeper. The first step of installing the shoring is to position the first outside panel. The location of this first panel is critical because the rest of the system will use it as a reference point. First, the crew puts a narrow bucket on the excavator and digs a trench for the plate to slide into. Then the first panel is carried into the excavation to be placed in the trench. It takes some trial and error to get the plate positioned in exactly the right spot. Once it's close, they use the excavator bucket to push the plate into the ground. And finally, the trench is backfilled to hold the panel in place with a few final adjustments from the excavator to get it plumb and true. The loader continues removing soil as needed, and the crew works to stage more pieces of the slide rail system. The next step is to install the first corner rail. Once secure, the second outer panel is next. These steel plates snap into the rail by starting at a 45-degree angle and rotating into place. That's easier than trying to lift each one all the way up and over the corner rails. In between installing each component of the system, the excavator and loader work together to remove more soil from the area. The crew hooks up the next corner rail to the excavator's arm and lifts it into place. Try to ignore your lazy host eating lunch in the background there. Once it drops in, the excavator again works to remove more soil from the hole. And now the third outer panel can be snapped into place. It's critical that this system be set up perfectly square, so the workers take the time to measure everything carefully. Then the third corner rail can go into place, quickly followed by the final outer panel, and the final corner rail. Now the system is locked together, but it's not ready for excavation just yet. Once all four rails and outer panels are in place, the sliding inner panels go in next. Where the outer panels will stay put to hold everything together, the inner panels will slide down the rails as the hole is excavated downward, providing support for the excavation and keeping it from collapsing. The crew has to work through a little rain to get these installed. It's a lot of work to install this shoring, especially when you consider how it's all going to be taken right back out. But when space is constrained like it is on this site, there just aren't many options to manage deep excavations, and there's no room for error when it comes to protecting workers in dangerous environments. Once the shoring system is in place, the crew can continue digging downward. The process is for the excavator to remove soil from inside the box, while the wheel loader carries the soil up and out of the way. As the bottom of the hole gets lower, the crew uses the excavator to push the panels and the corner rails of the shoring system downward to maintain support and keep the walls of the hole from collapsing. Sometimes all it takes is a little push. And sometimes advancing the slide rails requires something a bit more percussive. As the hole gets deeper, the excavator operator can no longer see what they're doing, so another member of the crew uses hand signals to guide the operation. Every so often, the excavator hammers on the inner panels to slide them farther downward toward the final depth of the excavation. When the hole has reached its final depth, surveyors descend to the bottom to do one last check of the elevation. A mistake here would affect every part of the project, so the crew makes sure their measurements are correct. Once confirmed, it's time to compact the subgrade. To make sure the underlying soil will serve as a strong foundation for the lift station wet well, it needs to be compacted in place. There's not a lot of room for heavy equipment in this deep excavation, so the crew lowers a miniature roller compactor down using the excavator. This machine uses vibrating drums with pad feet to densify and compact the soil. It's also remote controlled, so the operator can stay out of the hole while it runs, keeping him free from diesel fumes that could build up in the small confined area. It's not the fastest machine, but it doesn't take long at all to compact the entire bottom of the hole. The next step in the project is to place a working slab at the bottom of the excavation. This slab doesn't need forms at its edges, but it does need to be set at the exact right elevation. So, the crew sets boards inside the excavation that will serve as a reference during placement of the concrete. They use a measurement rod to get the elevation exactly right. This concrete pump truck arrives first to get set up. It extends its outriggers for added stability, and then it extends the boom. Before long, the first concrete truck arrives at the site. But before the concrete goes into the hopper of the pump truck, the pump has to be primed. A lubricant is run through the pump truck to coat the inside of the pipes and hose. The prime is discharged into the bucket of the loader for disposal, and now they're ready to place concrete. Rather than trying to drop the concrete into place from above using a chute, this pump truck makes it easy to put the concrete exactly where it needs to go. The operator communicates with the finishing crew and controls the position of the boom. Each new truck unloads concrete into the pump's hopper where it's pushed through the boom and the hose. Also known as a mud slab, the purpose of this working slab is to protect the soil at the bottom of the excavation during construction. Without it, this clay would turn into a muddy mess in the rain, making it unsuitable for supporting the lift station before the excavation is backfilled. Since its only job is to serve as a working platform during construction, it doesn't need any steel reinforcement or a perfect surface finish. It just needs to have the minimum thickness as required in the plans, and most importantly, to have the correct elevation for what comes next. The three-person finishing crew works together until they can't fit into the corner. One worker leaves, then two, until the last one is left to finish the job. Once the working slab is cured, everything's ready for the next step of the project. And that next step is going to require a crane. A big crane. This 300-ton capacity behemoth just showed up on site. It's an all-terrain crane, barely small enough to travel on roads and highways. Check out that all-wheel steering. To reduce its traveling weight, the crane comes with an entourage of flatbed semi-trucks carrying outrigger pads and counterweights. Rather than sit on its squishy rubber tires during operation, this crane uses outriggers to create a stable base and keep it from tipping. These steel plates distribute the load from the outriggers so that the underlying concrete doesn't crack or break and the soil below doesn't compress too much. This crane also uses counterweights to balance the forces on the slewing ring. It lifts each plate and stacks them behind the cab. Once the pile of counterweights is complete, they're pulled into place using a hydraulic mechanism. Now, the crane is ready for action. The primary component of this lift station is called the wet well. It's essentially a large concrete cylinder. Rather than cast the wet well in place, this project calls for precast segments that can be stacked together like Lego. And the first one of those segments has just arrived at the site. Crane Day is a big day, not just because of the size of the equipment on site. There's a lot that can go wrong when lifting and moving heavy loads, so there are a lot of people on site to make sure things run smoothly. It might seem like overkill, and it might seem like a lot of folks just standing around, but some days you have to hope for the best and plan for the worst. And spoiler alert, the only problem that happened this day was a flatbed truck carrying counterweights getting high-centered in the driveway. That's why the contractor decided to bring in another crane. This way, delivery trucks can stay on the road, get offloaded, and be on their way without any difficult maneuvering that might put a kink in the day's busy schedule. The first piece of the lift station's wet well is, naturally, the bottom. The rest of the wet well will sit on this concrete base. The crew takes it off the truck with the first crane, but before it's picked up by the big crane and set into place, it needs a little work. These concrete segments are designed to easily stack on top of each other. However, a concrete-to-concrete seal held together by gravity is not very watertight. And trust me, for large containers full of raw sewage, it's best that they don't leak. So, the crew is installing compressible gasket material anywhere concrete surfaces will mate together. And to make sure that everything slides together just right, they're also applying lubricant to the rubber gaskets. Once it's ready, the bottom segment is attached to the crane with chain slings and slowly swung around to the excavated area. Workers keep the heavy concrete slab under control using attached ropes called taglines as it's lowered toward the hole. Spotters keep a watchful eye on everything and everyone on site to maintain safety. The signal person is the eyes and ears of the operator. They use a combination of radio and sometimes hand signals to guide the motions and directions of the crane. Slow is the name of the game because sudden movements can cause the load to swing or crash into the side of the shoring. And even a little crash can be a big deal when you have as much momentum as this concrete slab. Once the bottom of the wet well is just above the mud slab, workers take measurements and communicate with the signal person to make tiny adjustments and get the slab in just the right place. When it's perfect, they make the call to set it down. Crews disconnect the slings so that the crane can move on to its next load. It's not the next wet well segment, but actually some heavy-duty tools to help workers guide each segment into place. These scissor lifts just barely fit into the corners of the excavation around the edges of the wet well, but they'll help the crew reach the higher joints and keep an eye on each segment as it's lowered into place. The next segment of the wet well is the first actual ring that will sit on the base. Just like the base, it arrives on a flatbed truck that needs to be offloaded by the small crane. And just like the base, it needs gaskets and lubricant to seal perfectly with the precast segments above and below it in the stack. Attaching the ring segments directly to the crane hook using chain slings would put too much horizontal force on the concrete, potentially causing cracks or breaks. Instead, the crew uses a spreader bar between the segment and the hook. This spreader keeps the forces in the chain slings vertical so they don't squeeze the concrete and cause undue stress during the lift. Once the segment is off the ground, the crew can lubricate the recess where it will slide onto the bottom slab. You can see smaller precast concrete manhole segments in the background there. Those will be installed in a future episode. Just like before, the segment is swung around to the excavation, then carefully lowered into the hole. The crew in the hole tells the signal person what they need, and he tells the crane operator what to do. Before long, the second segment is in place, resting comfortably on the base. Each following segment goes through essentially the same process. First, offload from the truck. Next, gaskets and lube it up. Then, hand off to the big crane and lower it into place. Disconnect, and send the crane back for the next one. Oh, and don't forget the pizza break for lunch. Each one of these segments weighs about 15 tons, roughly the weight of an average city bus. That's nothing to sneeze at, especially if it's hanging above your head. As the day wears on, the work starts to click into a predictable pace. Everyone has a job to do, and they anticipate the needs of others. The worksite gets quieter as everyone settles into the rhythm, and slowly but surely these massive pieces are installed one by one. When the penultimate segment goes into place, the scissor lifts can't reach any higher, so the mobile boom lifts come out to help the crew lower the final segment into place. This one is a little bit smaller than the others to make up the final height of the wet well. Eventually, this segment will be attached to the surface concrete slab and given an access hatch, but we're still quite a ways from then. And just like that, we have a wet well installed. It's a relatively minor milestone in the project, but a major accomplishment for the day to have everything go so smoothly and be able to be home by dinner. Even though the wet well is in place, that doesn't mean it's ready for the dirty job of holding raw wastewater. A crew lowers a scissor lift into the wet well to make it easier to access the inside walls. They install grout by hand into each of the joints between the precast segments to protect any exposed gaskets and help seal any potential leakage paths. Once the grout cures, it's painted with waterproof coating. This isn't the final protective coating that will go on the inside walls of the wet well, but it will work together with the grout at the joints to reduce the chance of leaks. To prove it, the wet well is required to go through a leak test before it's backfilled to make sure it's watertight. That's as simple as filling it to the brim with water and leaving it for several days. At the end of the test, if there's still water at the rim, minus an allowance for evaporation, and no visible leakage on the outside, the wet well is good to go. The crew did a little bit of epoxy injection into some small cracks as a precaution during the leak test. That's the source of the foam you can see floating on top of the water. After the required test period, the wet well was certified leak-free and ready for backfill. Backfilling this wet well isn't as simple as dumping dirt into the hole. It has to be carefully coordinated with the removal of the shoring system. Crews fight the rain getting ready to start this process, and they make sure to clean up the muck and mud in the bottom of the excavation because this hole won't actually be filled with soil, as you'll see. Since this shoring system was installed, the ground has had time to settle and shift, increasing the pressure on the panels holding it back. That means getting these panels out is going to be a little bit harder than it was to get them in. The contractor first uses the excavator to bump and push the shoring system around to loosen the panels and free them up. A hydraulic puller is connected to the inner plates to lift them up. But even that wasn't enough in some instances. The reaction forces required to pull these plates up along the guides with the friction of the soil they're holding back are tremendous. A few times, rather than lift the inner panel up, the hydraulic puller instead forced the outer shoring panel deeper into the ground, or bent the reaction beam. With a lot of persistence and a big excavator, they got the panels lifted enough and ready for the first layer of backfill. Rather than trying to compact soil into this tight area, the plans call for controlled low-strength material, also known as flowable fill. This is a slurry of cement, fine aggregate, and water that sets up like concrete, although with a lot less strength. It might sound strange at first to intentionally use a material with low strength, but it has an advantage because the contractor is going to have to trench through this backfill later in the project when the pipes are installed. It also saves a lot on cost. Conventional earthwork would be nearly impossible to do well in this narrow excavation, but flowable fill is considered self-compacting and it won't settle over time. It's used in all kinds of irregular excavations or voids like this where compacting earthen material would be difficult to impossible. In this case, they can pour the flowable fill directly into the excavated area using a wooden chute, and even the irregular areas behind the shoring panels are filled with material that will harden within a few hours and never settle over time. The backfill comes up in batches that equal a few feet or around a meter each, so that the shoring can maintain support of the excavation as the level comes up. The next batch of backfill follows a few days afterward. Now that the shoring system panels are loosened up, they can be lifted up with some gentle but persistent tugs of the excavator arm. This batch of flowable fill is being placed with a pump truck to make it easier to get all the way around the wet well, and the pump truck operator is already getting it set up. The panels are being lifted up just in time as mixer trucks are starting to arrive. Each truck unloads into the hopper of the pump and takes off right away to make room for the next one. The pump truck boom moves the hose to each corner of the excavation to place the flowable fill. There's a little bit of water in the hole, but it's not enough to cause any issues with this backfill operation. The controlled low-strength material continues to backfill the excavation, and all the while, the crew continues working on removing the shoring system for the hole. Over the next couple of days, the crew continues to remove elements of the shoring system from the excavation so that they can continue backfilling. Before the flowable fill trucks show up, the crew works to get the final panels pulled out. Rather than pull them all the way out before the previous layers of backfill set, some of these panels were left in the ground while the flowable fill cured. That balanced the earth pressure on the other side, making them easier to pull out. Getting them out last also makes the access a lot easier. They work on cleaning up the shoring system so it can be sent back. And they also clean up the excavation to remove loose soil so they can continue to backfill using flowable fill. And they're just in time for the trucks to start showing up. Mixer truck after mixer truck arrive to continue filling this hole up to the top of the second stage of excavation. Almost looks good enough to drink. Once that layer of fill is cured, it's time to start backfilling with soil. First, any uncompacted soil is removed from the excavation to make sure there are no loose pockets of dirt. The backfill soil is brought into the hole, spread out in an even layer called a lift, and then compacted into place. Every once in a while, a technician checks the backfill with a density gauge to make sure it meets the specifications. A lot of important parts of the project will eventually sit on top of this fill, so it's important that it won't settle over time. A surveyor comes out the next day to mark out the next step of the project. Even if it won't settle much, the compacted soil might settle a little bit, so the most important parts of the project will sit on flowable fill all the way up. It's just easier to backfill the entire area with soil and only carve out the spots that need to be flowable fill afterwards. An excavator carefully cuts away the areas that will eventually be backfilled with the flowable material. The next day, it's more flowable fill. Truck after truck arrive to backfill this excavated area just like a bathtub. It's almost hypnotic. All in all, it took 11 truckloads of flowable fill to finish out this part of the job. And the San Antonio River Authority's newest wet well is backfilled not far from where the ground surface will eventually be. There's still no sewer pipes yet. Right now, it's just a big concrete tank sitting in the ground. We still need to connect it to the sewage system. And the pipes that will make those connections possible were just delivered to the site. But they're not quite ready to install just yet. This wet well was backfilled using a material called flowable fill. It's a mixture of sand, cement, and water that acts kind of like a low-strength concrete. And here's why. Even though this material has to be strong enough to avoid settling over time, it also has to be soft enough to be excavated with machinery so that the pipes can be installed. It might seem odd to backfill the area before installing pipes, but it's much simpler to excavate narrow trenches for the pipes afterward rather than try to keep those areas open during backfill of the rest of the site. 3 lines will connect this wet well to the surrounding sewer system, which means 3 trenches need to be cut out. These trenches will need people working inside them to install the pipes. You can probably guess what they'll be using to keep those workers safe from a collapse or cave-in. Shoring will be installed where the depth or stability of the hole necessitates. These steel boxes arriving at the site will brace the walls of the trenches. They get put in place with the excavator before anyone can enter the hole. Since sewer pipes are often buried well below the ground, especially at lift stations where they terminate at the bottom of a slope, they have to withstand considerable pressure from the weight of the soil above. To make sure the pipe can carry these loads, the design calls for select backfill around the envelope of the pipe. This gravel being delivered to the site will be used as the bedding material. It's called bedding because it conforms around the pipe to provide support. The bottom of each trench gets a layer of gravel bedding where the sewer pipes will eventually sit. But before the pipes go into the trenches, they need a way into the wet well. You may have noticed there are no holes in the tank just yet. That's because the location of the pipes is critical. They work by gravity, so it's essential that they be installed at the right elevation to slope into the wet well exactly as required in the design. If the holes came pre-installed, there's a chance that a subtle shift or twist of one of the segments would cause them to be misaligned. It's just easier to drill them in the exact right spot once the wet well is installed and backfilled in its final place. The pipeline crew takes their time to confirm the measurements with surveying equipment and double-check each of the connections. You know the old saying, measure twice, core through a foot of solid concrete once. This is the core drill that will be used to create the penetrations. First, a small hole is drilled into the wet well, and a concrete anchor is installed. This allows the frame of the core drill to be temporarily bolted to the wall to keep it in the correct location. The drill is assembled on the frame, and before long, it's running. It's basically an overgrown version of the hole saws that you might have used on wood or drywall. The core drill uses water from a hose to lubricate and cool the hole saw and keep the concrete dust down. The saw is advanced by hand slowly but surely through the concrete wall. Eventually, it breaks through on the inside of the wet well. All that's left is a heavy chunk of the concrete core. That's hole number 1 finished, 2 more to go. The drill is assembled in the next location and put to work. It's not long before the second hole is done. The third penetration goes just as smoothly as the previous 2, and by the end of the day, the wet well is ready to be plumbed in. The gravel bedding in the first trench gets its finishing touches to make sure it's at the right elevation and there are no protruding rocks that could damage the pipe. Then the line is lowered into the trench. To create a watertight joint between the pipe and the concrete wet well, a link seal is installed around its perimeter. This device uses rubber links surrounded by plastic to seal the annular space between pipe and concrete. Tightening the screws compresses the rubber material, creating a long-lasting, watertight connection. A second length of pipe is lowered into the trench to connect to the first one. These plastic sewer pipes attach together using a bell and spigot design. The spigot end slides into the bell, which has a gasket that provides a watertight seal. First, the spigot has to be lubricated so that it doesn't damage the gasket as it slides in. The 2 sections of pipe are pulled together using a chain hoist, and eventually the backfill will keep them from sliding apart over time. The first sewer line actually won't connect to anything at all, at least for the time being. As this area continues to develop, there will likely come a time when a third lift station is needed to deliver all the wastewater uphill to the nearby treatment plant. The San Antonio River Authority and their engineer knew how quickly this area would grow, so they made sure to proactively upsize this wet well compared to its neighbor. When more capacity is inevitably needed in a few years, all they have to do is install some new pumps instead of a completely new wet well. But eventually, Phase 3 will come, and this pipe will allow the new lift station to connect to the one under construction right now. Until then, this one gets capped off. The solid PVC cap is pulled into place at the end of the pipe, and it's almost ready to be buried. That's the first pipe in, and it's time to move on to number 2. Since this trench isn't as deep, it doesn't require shoring. Just like the first line, gravel is spread into the trench to act as bedding for the pipe. A laser level is used to make sure the slope of this pipe matches what's required in the plans. Once the bedding's in place, the pipe is swung into the trench. That big black bulge in the middle of the pipe is a flexible coupling. Although the wet well has been designed not to move, even slight shifts from settlement, temperature changes, or structural loads could put stress on the connected pipes buried in the ground. These flexible couplings give each sewer line some freedom to move independently of the wet well, like a gross bendy straw, reducing stress on the pipe and the chance of a break. It's covered in plastic to protect it from the backfill material. A second length of pipe is added to the line. Then, the whole string is bumped into position using the excavator. You can get a good look at that link seal here. Once it's connected to the wet well, the loader brings bucketfuls of bedding material and dumps them on top to hold everything in place until they're ready to backfill the rest of the site. This pipe will eventually tie into a manhole that will connect it to the rest of the sewer system, so we'll be back here in a minute. The third line running to the new wet well will connect it to the system of the existing pumping station already installed on this site. These two facilities will work together to move raw wastewater to the nearby treatment plant. This third line needs to pass under the concrete of the existing lift station, and that's going to require a saw. This Crewe has a walk-behind saw with a diamond blade that can cut through the slab like butter. It connects to the water supply to lubricate and cool the blade, and to minimize the amount of concrete dust in the air. They follow the lines marked by the surveyor, then they break the concrete up into sections to make them easier to remove. Once the concrete is up, the Crewe can trench the third line. As the trench is cut, bedding gravel is added to the bottom just like the other two. And the shoring is dropped in to protect workers from a cave-in before they can enter the trench. Thick steel plates are used on top of this concrete when the trench isn't actively being worked on to allow vehicles to drive over when needed, and keep someone from accidentally falling in. Now that it's time to install the pipe, these plates get removed. The first pipe is lowered into the trench with the excavator. It's inserted into the last hole of the wet well, and then bedded down with gravel to hold the pipe in place. Once the plumbing is complete, the trench boxes can be removed. All three pipes get completely covered with the gravel bedding material that will provide even support. Since it's basically rock, the bedding material doesn't need to be compacted around the pipe, a process that might damage the plastic lines. Once the bedding is in place, shiny green warning tape is placed in the trenches. In the rare event that someone is excavating this area in the future, they should uncover the tape first to let them know there's an active sewer line not far below. Finally, the trenches get backfilled with soil to cover and protect the new sewer lines. Our old friend, the vibratory, remote-controlled trench roller, is back in action. It is kind of cute, but this roller compactor packs a strong punch, and it's the perfect size for working inside these trenches. A layer of backfill is added to the trench, and then it gets compacted into place. Every once in a while, a technician checks the density and moisture content of the backfill using a nuclear density gauge as a quality control measure. If the density were to be too low, the backfill would get another few passes from the compactor. Around the outside of the wet well, where a concrete slab will eventually sit, the engineer has specified that instead of compacted soil, the area be backfilled with flowable fill. But now, where it was trenched out for the sewer lines, it needs to be placed again. The site is a little bit of a mess at the moment, so instead of trying to get the mixer truck around the entire wet well, the crew instead just uses the excavator bucket to get to the spots where the chute can't reach. Where it can, the flowable fill is placed right into the hole. Watching flowable fill go in is one of my favorite things. And the excavator bucket pats the backfill into place just for good measure. Just like that, this project's sewer lines are connected to the wet well and backfilled. Now it's time to connect them to the rest of the sewer system. The crew starts excavating for the manholes where the new pipes will connect to the existing system. But take a look at this. That's not a leak in the sewer line. It's groundwater traveling through the soil and right into the newly excavated area. From there, it's moving into the new sewer line and right into the wet well. You never know what you'll find when digging deep holes in the ground, but at least it's a good test that the new sewer line is working correctly. The crew installs a pump to keep the site dry while the new manholes go in. The first manhole will connect the new lift station to the sewer that runs into the existing facility. First, the concrete is removed and the area is excavated down. The excavator works carefully to avoid damaging the line below. Every once in a while, a worker checks for the pipe. Once it's exposed and visible, the rest of the excavation goes smoothly. The shoring is the last piece before the manhole can be installed. This is a doghouse manhole, named because of the U-shaped holes that allow it to fit over existing wastewater pipes. That line is in service right now, carrying sewage into the existing lift station, so it can't be disturbed. The manhole fits over the new line and the existing sewer. The crew lowers it into place and checks to make sure it's level. But the manhole doesn't have a bottom, yet. It'll have to be cast in place with concrete. Concrete forms called falsework installed by the crew plug up areas where the concrete shouldn't flow, keeping the inside of the manhole tidy while the outside can be a little lumpy. Concrete is dumped into the manhole and around the outside. An immersion vibrator is used to get the air bubbles out and mobilize the concrete past the sewer pipes. It's hard to see the work going on inside, but this concrete will be smoothed and shaped to create a gentle path for the wastewater to flow. Here's a peek into one of the other manholes on site so you can see what it will look like when completed. While one crew works on this manhole, another continues backfilling the trench. Each layer of backfill gets compacted into place with the remote-controlled trench roller. Manhole number 2 also connects the lift station to an existing wastewater line. The crew carefully excavates downward to the line to avoid hitting and breaking it. A worker with a shovel checks every so often until they find the pipe. Once the old line is exposed, they can excavate for the last segment of new pipe and the final manhole of the project. Both lines that connect to the new wet well also have a plug valve installed. This will allow the river authority to divert wastewater to the other lift station when needed for repairs and maintenance. I'll show you how it all works once this manhole's installed. The last segment of pipe going to the new wet well gets lowered into place, measured, then cut to length. Finally, it's pushed into the bell to connect it to the rest of the line. Just like the previous one, this is a doghouse manhole that drops over the top of the sewer lines that it will connect. The crew works to install the falsework to hold back the concrete that will form the bottom of the manhole. You can also see the plug valve installed on the existing wastewater line. Once everything's ready, concrete is placed into the manhole and around the outsides to form the bottom. An immersion vibrator helps the concrete flow around the pipes. Again, this doesn't have to look pretty on the outside. It just has to form a stable bottom for the manhole and seal the areas around each of the sewer lines. Once the manhole bottoms are cured, each one gets a precast top segment that will eventually have an iron lid. And sealant tape is applied around the perimeter of each joint in the precast segments to prevent leaks. Those blue pipes hold the stems for the plug valves. Finally, the manhole bottoms and pipe segments get a leak test. Plugs are installed in the pipes where they terminate at the wet well. These get inflated to create a seal at the end of the line. Then each manhole is filled with water and left to make sure there are no leaks. Later, the pipes in the manholes will be cut so wastewater flows into each one, but for now, the pipes are left continuous so the manholes are bypassed during construction. Finally, I can show you how all this plumbing fits together. There's an existing wastewater line here that runs into this existing manhole. And there's another existing line that comes in from the opposite direction. Right now, they all flow into the wet well of this single existing lift station. But now, the San Antonio River Authority has options. The new line in manhole here, plus the two valves, means that all the wastewater from this line can be diverted into the new wet well. And the new line in manhole here means that all the wastewater from the other line can be diverted into the new wet well too. There's just one piece missing, and it just showed up in a truck. This monster plug valve is the last one needed to make these lift stations fully redundant. It will go on the 24-inch or 600mm diameter sewer line flowing into the existing lift station on this site. But you can't just turn off a functioning sewer line to install a valve. All the houses connected to this pipe are still using it 24/7. So how do you do a job like this and keep the wastewater flowing? A crew uses a diamond saw to cut out the concrete above where the line will be excavated. Then an excavator begins work to remove the soil above the line. Like all the trenches on this job, this one will need shoring to keep the soil from collapsing while crews are working inside. Eventually, the crew gets the line uncovered, but it can't be cut just yet. Remember that all the wastewater from the surrounding area has been collected and concentrated into a single pipe. This one. Before the valve is installed, all that sewage will need to be temporarily redirected. This bypass pump is just the right piece of equipment for the job. The crew lays out the hoses for the pump between an upstream manhole and the downstream lift station. Then they build a ramp so vehicles can get over the top. An inflatable plug will keep wastewater from flowing into the 24-inch or 600mm diameter sewer line while the valve gets installed. The pump will divert the wastewater straight into the lift station, bypassing the sewer line. A worker monitors the level of sewage in the manhole and regulates the bypass pumping to keep up with the wastewater flow. Meanwhile, a crew works to cut the existing line. Once a section of pipe has been removed, the valve can be lowered into place. This valve uses a mechanical joint to connect to the existing plastic pipe. Bolts connect a gland to the valve and compress a gasket between the two, pressing it tightly against the pipe to make a watertight seal. The crew finishes installing the valve with haste, and then they use gravel bedding to backfill the trench just like the rest of the underground piping on the project. At the new lift station across the site, it's time for more backfill. It might be hard to tell, but all of this work is still happening under what will be the final grade. Now that all the pipes are installed, the site needs to be brought up to its designed elevation. Anywhere that will eventually get concrete is backfilled with this select material. It's basically road base, crushed rock that interlocks and compacts into an extremely stable subgrade. The other parts of the site that won't be used to support any structures can be backfilled with the native clay. First, the materials spread out in an even layer called a lift. Then the roller compacts it into place. An inspector checks the density of the backfill as a quality control measure. A hole is hammered into the new compacted soil using a metal pin. Then the tester pushes a source rod into the hole. This rod has a radioactive source on the tip, and actually requires a license to operate one of these gauges, but backfill is important. A lot of expensive stuff is going to sit on this material, and we don't want it settling over time. The nuclear gauge can calculate the density and water content of the soil based on how much of the source radioactivity makes it through to the sensor above the surface. Most of the underground work is done by now, but not all of it. This lift station will use some pretty big pumps, which means it needs robust electrical connections. The conductors between the pumps will run in underground conduits. First, the trenches are shored for safety. Then the bedding gravel goes in to provide even support to the conduits once they're buried. With the conduits installed, a layer of red concrete goes in. The red color is an extra precaution to warn anyone digging in the future that there are electrified lines below. Finally, the trenches are backfilled with select fill and compacted to prepare for construction of the control shelter. They use a vibratory plate compactor around the larger areas and a tamping rammer, also known as a jumping jack compactor, to get into the tighter spaces. At this point, there's a lot happening all at once on site, so don't mind if I show a few things out of order to keep the story clear. Construction schedules are rarely designed with narrative structure in mind. This area will eventually get a concrete slab and a steel shelter to protect the lift station's electrical equipment and controls. The shelter will be supported by 3 posts concreted into these holes in the ground. The crew works to install the concrete forms that will make up the post's foundations and compact the surrounding soil to create a firm base. Each form tube is checked for level and elevation before it's secured into place with backfill. Each hole will also get steel reinforcement before the concrete is placed. This rebar helps the concrete foundation resist forces like wind loads that the shelter will be subject to. Once the posts have been installed and concreted into place, the crew works on forming the rest of the shelter pad. They install formwork around the edges, tie reinforcing steel to be embedded in the slab, and form around locations where electrical conduit comes up from underground. And before long, it's time for the concrete trucks. Concrete is placed into the forms using the chute on the truck. It's spread roughly into place with shovels. Then a screed board sets the top surface. Once all the concrete is in, a magnesium float is used to smooth the surface and embed the large aggregate in the concrete. The bull float has a tilting mechanism that makes it easy to smooth the concrete in both directions, pushing and pulling. Then the slab is left to cure. It's a little hard to see with the concrete in, but the entire perimeter of formwork is lined with these little wooden triangles called chamfer strips. When the formwork is removed from the slab, you can see the nice 45-degree corners, or chamfers, these strips create. The chamfers not only improve the appearance of the slabs, but they reduce the chances of the corners chipping or breaking over time, extending the lifespan of the pad. Once the slab's complete, the rest of the shelter can be installed. Steel sheets are attached all along the roof and the back wall. These sheets will eventually protect the electrical equipment panels from sun and weather. We'll come back to the shelter when the electricians have made some progress on those panels. Right now, there's more concrete to place. The area between the wet well and the new shelter will eventually have all the discharge piping from the pumps and other equipment above ground. But first, it needs a concrete slab. The crew finishes compacting the subgrade below the slab and checks the level using a laser. Just like the electrical shelter, this equipment slab starts with formwork around the perimeter and a mat of reinforcing steel. The concrete arrives on site. However, before it goes into the forms, a little bit goes into a wheelbarrow for the testing lab. How do we know that the concrete delivered to a construction site actually meets the specifications required by the engineer? We have to do quality control tests, or at least a technician on site does. First, the technician performs a test to check the workability or consistency of the mix called a slump test. A cone is filled with the concrete and rotted to remove air bubbles. Then the cone is lifted, allowing the concrete to slump. The distance from the top of the cone to the top of the concrete is measured, and this must be within the allowable guidelines. Too little slump and the concrete won't flow easily into the forms. Too much slump may be a sign that the concrete has been improperly mixed. This test also helps verify that the concrete across multiple trucks has similar properties. Next, the technician checks the air content of the concrete. The air meter applies pressure to the concrete sample, compressing the bubbles within the mix so that the change in volume can be measured. Not enough air entrained in the concrete can make it brittle and subject to flaking, especially under freezing conditions. Too much air can make the concrete difficult to finish and create surface defects. Finally, the technician uses plastic molds to form concrete cylinders. These cylinders will eventually undergo compression testing after they've had time to cure to make sure that the concrete is as strong as required by the engineer. If the concrete company made an error in a batch they sent to the site, it would be caught by one of these tests, and the slab would have to be taken out and redone. Luckily, all the concrete on this project passed quality control with flying colors. This equipment slab is placed just like the one at the electrical shelter. Just before the concrete is too stiff, a broom is run along the surface to provide a non-slip texture to the slab. That's another one done on this project, but we're still far from finished with concrete. The next task is the light pole. Like the shelter, this pole will be supported using a drilled concrete shaft. And the drill just arrived in a pickup truck. Skid steers are versatile little machines, and this one has been equipped with a miniature drill rig. The surveyor has already marked the center point of the hole, and now it's time to drill out the soil so the concrete can be installed. The process is simple. Spin the auger until the soil is broken up in the hole, pull it out and shake it off. Then do it again. And again. It doesn't take long at all to reach the final depth of the hole, almost as deep as this little auger can reach. Then a trench is dug to run the power lines through conduit to the light. Reinforcing steel is placed inside the hole, and a cardboard tube is used to form the pier above the ground. This will get concrete in a moment. Meanwhile, workers are making progress forming the slab over the top of the wet well. First, scaffolding will have to be assembled within the wet well. Something has to support the underside of the concrete slab while it's cast in place, so scaffolding is erected inside the wet well to provide the support. All this scaffolding will have to be removed through the access hatch once the concrete is cured, so all this has to be easy to disassemble when the time comes. Finally, the carpenters install a plywood false cover over the top of the wet well that will form the bottom of the concrete slab. Unlike the equipment slab, that is essentially a continuous area of concrete, the wet well cover slab has a lot of embedded items. In addition to the formwork, it gets blockouts for the vent pipe, the stilling well, each of the 3 discharge lines for the pumps, a suction line for the backup diesel pump, and vent line for the air release valve. Don't worry if all this equipment means nothing to you right now. I'll show you what all of it does when it's installed. Of course, the biggest blockout is the access hatch that will allow people and equipment to get into and out of the wet well once the project's finished. The access hatch is placed where it will be embedded in the concrete slab. Then it's secured into place so that it doesn't shift during the concrete pour. One challenge with the concrete slab above the wet well is that it needs to stay attached to that structure no matter what. If the heavy concrete wet well settles over time, we don't want the slab on top being separated from the rest of the structure. The project structural engineer developed a pretty cool way to make sure these 2 components of the project act as one. And it involves a lot of cardboard. These are void forms designed to fit perfectly within the space of the wet well cover slab. Well, perfectly with a bit of excavation. This shot is a perfect reminder of how strong the select backfill can be. That angular crushed rock compacts so tightly, you need a hammer drill to break it loose. The void forms were manufactured and delivered to the site already built, so it's kind of like a puzzle getting them all to fit just right. These cardboard forms are strong enough to hold up the concrete while it cures, but they will quickly deteriorate, leaving an empty space below the slab. The concrete is designed to only be supported by the perimeter of the wet well itself. That ensures that if the wet well settles over time, the slab will settle too, without experiencing undue stress from the underlying subgrade pushing back upward. If you had a careful eye, you may have caught these retaining blocks being cast on site using some simple carpentry for molds. We called them pavers since they look like stepping stones you might buy at the hardware store. Once they're cured, the retaining blocks get placed all around the formwork for the wet well cover slab. After the cardboard void forms deteriorate, they leave an empty space between the concrete slab and the subgrade, which is an issue around the edges. We don't want soil collapsing into the void that's left behind, or any animals getting in there either. So the project requires these precast concrete retainers be installed all around the perimeter of the wet well slab. When the cardboard dissolves, these will keep soil from filling the void while still allowing the slab some freedom to move up or down with the wet well. The reinforcing steel is installed inside the forms. That gets an inspection to make sure it conforms to the engineered plans. And finally, it's time to place the concrete. All that reinforcing steel is needed to make sure the slab can cantilever out past the wet well, since it won't be supported from underneath once the cardboard dissolves. And all the blockouts, electrical conduits, and the access hatch are secured in place. The concrete is spread into place with rakes, and it's vibrated to help it consolidate and flow around the dense mesh of rebar. You can see the air bubbles coming up out of the concrete as it's vibrated into place. The finishing crew carefully floats the surface all around the penetrations. The foundation for the light pole gets concrete in the drilled hole, and then it gets more concrete in the trench carrying the electrical conduit that will deliver power to the light. This is a perfect example of the pace of heavy construction. It's taken days and weeks of hard work to get this light pole and wet well cover slab formed and ready for concrete, and then the trucks and finishing crews arrive and are done with the pour before lunchtime. A few more structures need to be installed before the concrete on this job is mostly over. One is the slab that will hold a diesel pump that can be turned on in the event of an emergency or power outage when the main pumps are out of service. The subgrade below the slab gets backfilled and compacted. Electrical conduits are installed that will carry the control cables. Then the concrete can go in. The wet well also gets an electrical rack to hold all the connections between the panels, sensors, and pumps. There will also be an outlet here for any equipment needed to service the wet well when it's complete. The conduits stub up from their underground trenches and the wet well cover slab here. The carpenters assemble the formwork, and the fresh concrete is placed inside. Once the concrete is cured, the forms are stripped off these slabs and they get compacted backfill around the sides. Before long, the electricians have the rack and junction boxes installed at the wet well. And while they're backfilling, the crews finish installing those concrete retainers. You can really see how soil might collapse into the void forms below the wet well lid without them. Another concrete placement is for a curb that surrounds the diesel pump slab. If the pump ever leaks fuel, this curb will keep the diesel from contaminating the adjacent soil. A pipe with a valve makes it possible to drain the containment area of rainwater. The last place we need some concrete, for now, is at the new manholes. The cast iron covers have already been installed on the concrete manholes, and now they need concrete around the rim and valve box covers. This area is backfilled with select material, compacted, and formed. Then the concrete is placed as required in the plans. Remember that these manholes aren't doing anything yet. The active sewer lines are still running straight through them with no connection. One thing that's needed before those lines can be cut is on its way, but they need to be cleaned out first. A crew power washes the inside of both manholes and the wet well in preparation for what's next. That's the job of this box truck pulling into the site. If sewage decomposes without a good supply of fresh air, it can generate hydrogen sulfide gas. This gas is not only poisonous, but also extremely corrosive to steel and concrete. To protect these new structures from the challenging environment in a wastewater system, the walls and floor of the manholes and lift station wet well will get a spray-on epoxy liner. The worker dons a protective suit and respirator before descending into each manhole to apply the coating. The gun mixes the two-part epoxy right before it exits the nozzle. Touch-ups are applied topside. Next, another worker uses a trowel to smooth the lining and ensure consistent coverage. It only takes a few hours for the epoxy to fully cure and harden. The parts of the wet well that won't be lined are masked off first. Then the spray lining is applied to the inside walls. The worker checks the thickness of the wet epoxy to make sure he's applying the right amount. The manholes and wet well are now considered confined spaces, so there are special safety precautions about working inside them. The crew uses a gas meter to check for a hazardous atmosphere. They use ventilation fans to keep fresh air flowing. They have a rescue winch installed to lift the worker out of the hole if anything were to happen. And they have a spotter whose only job is to keep an eye on the worker inside to make sure they're staying safe. Before long, the entire wet well walls are lined with the protective coating. The masking is removed from the access hatch, and this team will be back once the bottom of the wet well is finished to complete the job. The concrete slabs are almost all complete. The manholes are ready for wastewater, the electrical shelter is ready for equipment, and the wet well is ready for pumps. Seems like a lot is left to be done, but these last steps of the project will happen before you know it. Pipes are arriving on site to the San Antonio River Authority's newest wastewater lift station. Now that most of the underground work is done, it's time to start installing the equipment that will connect the wet well to the uphill treatment plant. The pipes arrive with a protective coating that, in most cases, needs to be removed. The sandblasting rig is here, and so is the sand that will be used to clean these pipes and get them ready for paint. The process of sandblasting, also called abrasive media blasting, uses compressed air to fire media through a hose. In this case, the media is sand, but there are lots of other materials that can be sent through a hose with compressed air. All the steel pipes for the project are blasted clean of the protective factory coating. This gives the flanges fresh surfaces so they will seal together correctly, and it cleans and roughens the outside of the pipes to prepare them for final coating. Once blasted clean, the pipes are ready to be painted, but you rarely hear it called that in the field. Paint used to protect metal surfaces is mostly just called coating by the pros. This spray painting rig also uses a pressurized air supply from a trailer-mounted compressor to deliver paint to the nozzle. All the pipes and fittings are masked off to make sure none of the coating gets on the flanges or inside. Then they're set up on sawhorses and coated. All the fittings and reducers get coated as well. But we don't just hope the coating meets the project specifications, we double check. This is a dry film thickness gauge that uses a magnet to measure how much paint is built up around the pipe. Turn the wheel until the indicator pops up and it tells you the coating thickness in mils, which are thousandths of an inch, or about 25 microns. Once confirmed that the coating meets specifications, it's almost time to start installing the pipes. The very first lines will go into the wet well, but the scaffolding inside has to be removed before that. This assembly has been useful to hold up the formwork while the concrete top was cast, and for the spray liners to stand on while they did their work, but now it's in the way. It gets dismantled inside the wet well, and each piece is lifted out one by one. While one crew gets the last pieces of scaffolding out, another starts laying out the locations for all the pipes using string lines. The strings make it easier to get nice straight lines as pipes, fittings, and valves are moved into position. And plumb lines mark the locations at the bottom of the wet well directly below each of the 3 blockouts in the concrete lid at the top. A lot of these pipes are quite heavy, so the mobile crane is brought back to the site one more time to help lift them into place. It gets into position, and then the operator puts down the outriggers to help create a stable base. And finally, it's time to start installing pipes. The first discharge line is lowered into the wet well through the hatch. It's attached to a special quick-release connection system already installed at the bottom of the wet well. The next section of the first discharge line is lowered into the wet well through the hatch. It's set at the bottom of the wet well, then re-rigged through the concrete blockout at the top and lifted into place. Once positioned correctly, the flanges are bolted together. This gets repeated for the other 2 discharge lines. The first pipe is lowered into the wet well and attached to the pump discharge quick release. Then the second line is put in, disconnected, reattached through the blockout, and lifted into place. The space between each of the discharge lines and the concrete blockout are filled with link seals just like the sewer lines coming into the wet well. Before long, it's time to start connecting the above ground sections of pipe. These pipes will sit on supports that are bolted into the concrete pad. Holes are drilled, and then anchors get epoxied into the holes. Once cured, the anchors will hold each pipe support rigidly to the slab. Most of the above ground piping and fittings come together using flanges. A gasket between the flanges creates a pressure-rated seal, and the ring of nuts and bolts hold each pipe section tightly to its neighbor. All these pipes and fittings come together pretty quickly, but it'll be easiest to understand them if we go in order. I'll walk you through the whole assembly in a minute, but I want to start with the pumps, and they haven't been installed in the wet well just yet. Before they go in, the bottom needs a little work. Since the pumps will be installed near the center of the wet well, the outside corners could be an area where solids accumulate. The engineer specified that the bottom of the wet well be sloped toward the pumps in a bowl shape to make sure there are no stagnant areas where solids might settle out of suspension. And that's going to take some more concrete. A concrete pump arrives to the site and gets set up by extending its boom. The truck lowers a hose into the wet well, and a finishing crew works to get the new bottom perfectly sloped toward where the pumps will eventually sit. Once this concrete cures, the coating crew returns to finish up the epoxy liner at the bottom of the wet well. And finally, it's time to put in the pumps. Each of these pumps is rated to use 50 kilowatts or 67 horsepower of electricity to move around 800 gallons or 3,000 liters per minute to an elevation of around 200 feet or 60 meters above this lift station. And there will be 3 of them in the wet well. These pumps are specifically designed for sewage applications. The San Antonio River Authority hopes that no one would put anything except water, human waste, and toilet paper into the sewage system, and especially not wipes. But in the case that something larger or more fibrous finds its way to this lift station, the impellers in the pumps have a special shape to avoid getting caught on stringy debris. And if a pump does get clogged, each one can be disconnected from the discharge line and lifted with a chain out of the wet well for service. That means installing these pumps for the first time is a pretty simple job. Each pump has a knuckle that fits into vertical guides that run along the discharge pipes. A hoist or crane simply lowers the pump along the guides. When the pump reaches the bottom, it seals against the discharge line with its own weight, providing a pressure-rated connection without having to send someone to the bottom of the wet well to tighten bolts. Each of the pump's chains is hooked at the top of the hatch to make it easy to remove a pump from the wet well for inspection or service. And the electrical cables are securely attached there as well. Those electrical connections run in conduits through the concrete and up to the junction boxes where they're attached to the rest of the control system. Part of the job of the control system is to know when to turn the pumps on, so this wet well needs a liquid level sensor. The sensor is installed inside a stilling well, a length of pipe inside the wet well meant to isolate the sensor from any splashing or waves that happen from the wastewater flow. This is really just a length of PVC pipe that extends almost the entire height of the wet well. You can see the stilling well at the top right in this shot as crews start to fill the wet well with water for its first test. And you can see the float switches installed as well. If the level sensor stops working or something else goes wrong, these simple float switches will set off an alarm and flash a light at the top of the control shelter to let operators know that the level is too low, which could cause the pumps to run dry and overheat, or too high, which could cause a backup in one or more of the sewer lines or an overflow. The wet well also gets a gooseneck vent to equalize the air pressure inside and out. This water's just for testing the pumps, but before long, wastewater will start flowing into this wet well from the surrounding sewer lines. When the liquid reaches a prescribed level, it will trigger the control system to automatically turn on one of the pumps, called the lead pump. And if the level keeps going up, a second pump, called the lag pump, will turn on too. This lead-lag configuration helps the station account for variable flow rates, and the third pump acts as a standby. The lead pump, lag pump, and standby alternate so that they wear down evenly over time. Each pump has its own discharge line we saw be installed that comes up through the concrete to an above-ground manifold. First, the lines are each equipped with a pressure gauge that makes it easy to see if a pump is running, and if so, at the right pressure. Then each line gets a check valve that only allows flow in one direction. This valve prevents one pump from simply backflowing wastewater into the wet well through another pump's discharge line. Next, the lines each have plug valves so they can be isolated for maintenance. Pipes and valves don't last forever, so everything in this facility has been designed to make it easy to service parts and keep things up and running. After the isolation valves, all the individual lines come together into a single pipe that passes through an automatic air release valve. Air bubbles that get into the line can get stuck at this high point and constrict the flow. This valve uses weights and a float to automatically release air from the line without letting any of the wastewater out. As you might imagine, air bleeding from a pipe full of raw sewage isn't exactly pleasant to smell, so the air bleed line runs right back to the wet well. This also keeps wastewater from leaking onto the ground if this valve were to malfunction. And just like this facility is designed for ease of maintenance, it's also designed with lots of redundancy. The 3 pumps are just the start. Sewage keeps flowing, even during emergencies and power outages, so this pump station is designed with contingencies. A 4th pump, this one powered by diesel, can keep the wastewater flowing if this facility loses grid power. And now, it's time to put the pump in place. The diesel pump has a suction line installed in the wet well you can see here, and its discharge line runs to the above ground manifold with a check valve and plug valve like the others. But even if all 4 pumps are out of service, the manifold also includes an emergency bypass so that the San Antonio River Authority could bring in another mobile pump, hook it up quickly, and avoid a backup or overflow. All 5 pump discharge lines come together ahead of the flow meter that keeps an accurate record of how much fluid passes through the pipes each day. Operators can compare the readings on this meter to the ones at the end of the line to make sure there are no leaks or equipment malfunctions between the two. One last plug valve makes it possible to isolate the entire facility for maintenance, and then wastewater leaves the pump station into the force main. This is a pressure-rated sewer line that was installed during construction of the original lift station, and now it's time to connect it to the new facility. Crews extended this line toward the new pump station earlier in the project, but waited for the final pieces until the discharge manifold was finalized. They install elbows to turn the corner. Each connection is attached with a compression fitting called a mechanical joint. The final length of underground pipe is installed. Then, concrete is placed at each of the bends to create structures called thrust blocks that will distribute the pressure into the soil and keep the pipe from moving over time. The metal pipe is wrapped in plastic. All the underground piping is backfilled. And now this lift station has a direct connection to the wastewater treatment plant nearby. In many ways, a wet well type lift station is just like a sump pump in your basement. Triggers a float switch, the pump comes on, and the water level drops back down. But in many ways, this facility is not anything like a basement sump pump, and most of those ways are electrical. Let's take a look at the power and control systems of the pump station. Both the original lift station on this site and the new one are fed power from the grid through these new 480-volt transformers installed by the electric utility. Each of the 3 phases runs through a disconnect switch, allowing the entire facility to be isolated from the grid, a meter so the utility can bill for power usage, and then a fused switch that will protect the equipment in the event of a short circuit. Each of these monster fuses is rated for 350 amps at 500 volts. That's a lot of power. From there, power hits to the control shelter and its panels. Another disconnect switch allows the new pump station to be isolated for maintenance, and then a transfer switch is installed. Again, it's all about redundancy. If the power goes out, the San Antonio River Authority can bring in a mobile generator and connect it directly to the equipment here, flip the transfer switch, and power the lift station off-grid. And a transformer converts the 480-volt service to 120 volts for the lights, outlets, and other controls. Of course, a high voltage facility like this needs a robust connection to the ground to protect workers and make sure that a fault can be identified quickly. Copper rods are hammered deep into the ground and welded to the conductors to create a good bond. The entire grounding system gets tested to make sure it's well connected to the earth. A small current is run between the ground rods and a test electrode on the other side of the construction site, and the resistance between the two is recorded. If the resistance were too high, more ground rods would have to be installed, but the system passed the test just fine. This panel houses the remote terminal unit for the San Antonio River Authority's Supervisory Control and Data Acquisition, or SCADA system. Rather than send someone to this lift station to record data or change the controls, it's easier to pipe everything to a centralized location. SCADA is a type of industrial network that interconnects sensors, controls, and databases to keep accurate records and enable remote control of facilities like this one. An antenna at the top of the shelter gives the lift station a wireless connection, and the remote terminal unit provides an interface for an operator at the lift station. But that doesn't mean there aren't manual controls. This is the pump control panel that allows an operator to start and stop each of the 3 pumps. It includes circuitry to soft start each one to avoid huge power surges, cycle through the pumps so they wear evenly, and error systems to shut down a pump if it overheats or loses a seal. The panel next to it has the circuit breakers for each pump to protect them against short circuits. These panels connect to the pumps through underground conduits. The electricians had a pretty clever way to run the cables through. First, they tie a plastic bag on a string and suck it to the other side with a vacuum. Then the cables can be tied to the string and pulled through each conduit. Once all the electrical work is done, this project is getting close to wrapping up. The contractor starts cleaning up the site to prepare for the last items. One of those items is installing bollards to protect the lift station from an errant vehicle. They attached drilled concrete piles to create a strong and sturdy foundation. Then the last concrete of the job goes in. This slab connects the new lift station to the old one, creating a drivable area for maintenance personnel and operators. They also replaced the concrete that was removed to trench in one of the sewer lines below the original pump station. The bollards are installed, and the concrete is complete. Now all that's left is to get this facility in operation. The first test of the pumps won't be sewage, but water from the city distribution system. If something goes wrong, it's a lot easier to fix it before the sewage hits the proverbial fan. The hose goes into the wet well, and it slowly starts to fill up for the test. On testing day, the plan is simple. Turn on each of the pumps to confirm it's operating as designed. The pump manufacturer has a representative on site to help with the process. Each pump is turned on. They check the pressure on the gauge to make sure it's right. And they check the flow meter to ensure the pump is moving the right amount of fluid out of the wet well. You can easily see the level in the wet well dropping as each pump is turned on. Finally, they run the emergency diesel pump to confirm it's working as well. It sounds easier than it really is to check everything in this sophisticated facility and confirm it's working properly for the very first time, but before long, all the equipment passes the checks with flying colors. It's been almost an entire year of work to get the San Antonio River Authority's newest lift station built and running. We followed the process from the first scoop of dirt until now. And if you look closely, you can see how much the surrounding area grew just during that time. Those new developments and new houses will depend on this pumping station to carry wastewater away to the uphill treatment plant. All the people who live and work in this area might not ever even know it's there, and that's kind of the point. We want our sewage to be out of mind and out of sight. But I hope you've enjoyed getting an up-close look at what it really takes to keep our modern world running and all the hard work that goes into even the most hidden parts of our constructed environment. Huge thanks to the San Antonio River Authority for inviting us onto their project, their engineer UEG for fielding all our questions about the design, and their contractor, MGC, and all their subs for putting up with us on the job site to document the process. It really is not a small thing to have a film crew watching you work, especially when your job is hard enough as it is. Thanks to our streaming partner Nebula, where you can watch the whole series ad-free at the link below, and huge thanks to the practical engineering team who made this series possible. There's a relatively new term in Italian, umarell. I'm sure I'm pronouncing that wrong, but it refers to retired people who spend their days watching construction sites. I really believe we all deserve to be those old pensioners, seeing how the world gets built around us firsthand. And documenting the construction of heavy civil infrastructure has been a dream of mine for a long time. It took a ton of work from everyone involved to make it happen, but hopefully we made it look effortless. What do you think? I really do want to hear your feedback, so shoot me an email or leave a comment below. Thank you for watching, and let me know what you think.